In August of last year, Anthropic took a group of employees, not robotics experts, just regular staff, into a warehouse with an off-the-shelf robot dog. Half the group got access to Claude, half did not. The task, get the robot to autonomously fetch a beach ball. The team with Claude did better, faster, more capable, fewer dead ends. But here's the detail that mattered most. Before the experiment even started, Anthropic checked whether Claude could just do the whole thing by itself, with no human involved, at all. It couldn't. It got stuck on the very first step, figuring out how to connect to the robot. That was 10 months ago. Anthropic just published Phase 2 of this experiment, called Project Fetch. And this time, they tested whether their newest model, Claude Opus 4.7, could do the entire thing alone, with no human help. It didn't just succeed, it was on average 20 times faster than the fastest human team from last year. This video covers exactly what happened, the real numbers, where Claude still struggled, and what Anthropic thinks this means for the future of AI controlling physical machines. Here's exactly what the original Project Fetch involved. Because understanding the task list is what makes the result land. 6 steps, building on each other. Operate the robot dog using its manufacturer-provided controller. Connect to its onboard video camera. Connect to its LiDAR sensor, the system it uses to sense distance and obstacles. Write a program to manually control the robot through code, rather than the controller. Build a way to track the robot's position as it moves through space. Write a program that can detect a beach ball using the camera feed. And finally, combine everything into one system that can autonomously find and retrieve the ball with no human input. For Phase 2, the rules were specific. Claude couldn't physically hold a controller, that part of the test wasn't repeated. Instead, Anthropic ran 3 separate trials of Claude Opus 4.7, using Claude code with thinking effort set to maximum. The only human involvement was genuinely minimal. Someone plugged a laptop running Claude code into the robot, typed the first instruction, and then approved each command and each step forward. Claude did everything else, writing the code, connecting to sensors, interpreting camera data, building the tracking system. On the 4 tasks that both human teams completed last year, here are the real timing numbers, directly from Anthropic's report. The team without Claude, 361 minutes, just over 6 hours. The team with Claude assisting them, 181 minutes, about 3 hours, roughly half the time. Claude Opus 4.7, working completely alone with no human assistance, 9 minutes and 35 seconds. 9 minutes, for tasks that took a human team with Claude's help, 3 hours. That's 18.9 times faster than the human plus Claude team, and 37.7 times faster than the unassisted human team. On the broader set of 5 tasks, including connecting to the camera and LiDAR sensors, the comparison holds. The unassisted human team didn't manage to finish all 5. The Claude-assisted team completed them in 264 minutes. Opus 4.7, averaged across 3 separate trials, completed them in 12 minutes and 7 seconds. And here's a detail that matters as much as the speed. Opus 4.7 did this, while writing dramatically less code. The human team working with Claude last year produced just over 10,000 lines of code to solve these tasks. Opus 4.7, working alone this time, used just over 1,000 lines, roughly 10 times less while matching or exceeding what both human teams achieved. The speed difference wasn't really about typing code faster, it was about decision-making. Anthropic's report is specific on this point, where the human team struggled to choose between multiple different approaches to interface with the robot's sensors, debating options, trying one thing, backtracking, trying another. Opus 4.7 was able to quickly identify the best path and commit to it. Much of the code it wrote worked correctly on the first attempt, which was not true for either human team in the original experiment. That is the actual capability being measured here. Not raw processing speed, decision quality under uncertainty, applied to a genuinely novel physical system the model had never specifically been trained on. The robot dog, its particular sensor setup, the warehouse environment, none of that was something Claude had seen before. It had to figure out the right approach from general knowledge and reasoning, the same way a skilled engineer would, just much faster. Claude wasn't flawless. The report notes it defaulted to using an outdated object detection algorithm for the beach ball finding task, but even with that misstep, it found a workaround and reached a working solution, which is itself a meaningful capability, recognizing a dead end and adapting, rather than getting permanently stuck. This is the part of the story most coverage will skip, and it's the part that makes the result credible rather than hype. The final task, the actual fetching in Project Fetch, was the one place Claude did not succeed. The task required nudging a beach ball with the robot's body back to a home base, a patch of fake grass where the robot started. That requires a tight feedback loop, noticing the ball has drifted off course, understanding how your last movement caused that, figuring out where the ball is now, and adjusting the next movement precisely. Humans, after some trial and error, got reasonably good at this. Claude could position the robot behind the ball and attempt to knock it toward the target, but the execution was poorly controlled, not precise enough to reliably succeed. In Anthropic's own words, this was a struggle Claude shared with the human participants who reached this stage. It is a hard problem. Worth noting, one Anthropic researcher with more robotics experience than the original Phase 1 volunteers did successfully write a program for autonomous fetching. Anthropic believes that with more time and better scaffolding, current Claude models likely could do the same. The open question isn't whether it's possible, it's whether Claude can do it with the same speed and reliability it showed on every other task in this experiment. Anthropic frames this result around a pattern they say they've now seen twice. First, AI models are helpful to humans doing a task. Then, humans become helpful to the models, providing oversight, correction, guidance. Finally, the models become capable of doing the task largely on their own. They saw this exact progression in cybersecurity, which is the backstory behind Claude Mythos, the model with cybersecurity capabilities considered too dangerous for general release. Now they're describing the same arc playing out at the boundary between AI and the physical world. The comparison Anthropic draws is to agentic coding. AI models first used existing software, like simple text editing commands, to gradually become capable of complex autonomous coding work. Project Fetch suggests a similar transition might be starting with physical tools, AI systems using off-the-shelf hardware built for humans with reasonable competence. To be clear about the limits here, this is not robotics being solved. None of these tasks involve the genuinely hard, low-level problems of robotic control, things like developing a precise actuation policy for a specific physical movement. Claude used existing tools and wrote software to interface with them. It did not design new, physical capabilities or solve novel mechanical engineering problems. The beach ball task, the one requiring genuine real-time physical precision, is exactly where that distinction showed up as a real limitation. Anthropic's own framing is appropriately cautious. We may be entering the early era of what they call physical agentic AI, but how far this generalizes, and whether there are real barriers ahead, remains genuinely open. What is clear is the pace, capability gaps that looked large a year ago have closed faster than expected. Anthropic's own line on this is worth repeating directly. Models building their own software tools once seemed outlandish, and it's happening. They suggest it would be unwise to assume the same can't happen in hardware. Anthropic's full report, including the real video footage of Opus 4.7 controlling the robot, and the bar charts behind every number in this video, is linked in the description below. If you want to understand the broader context of what Anthropic is building right now, including the $965 billion valuation in Claude Opus 4.8, those videos are linked in the description. Subscribe for weekly coverage of what's actually happening in AI. Thanks for watching.